Hello friends, now let's try to solve the most storms removed with same rule or column problem. Let's see the statement. On a 2D plane, we place stones at some integer coordinate points. Each coordinate point may have at most one stone. Now a move consists of removing a stone that shares a column or rule with another stone on the grid. What's the largest possible number of moves we can make? Let's see the examples. The first example, we are given 6 coordinates of the stones, and we output 5. Let's see the picture. I draw the picture. This is the 6 stones, and we can do the moves because they share the same column rows, and we can see this is one connected component. So the total moves we can make is the total stones minus the number of the connected components, and we get 5. And let's see the second example. We are given the 5 stones and their coordinates. Finally, we output 3. You see, this is the 5 stones, and then we can connected these 4 stones, and so in the picture there are 2 connected components, and the total moves is the total number minus the number of the connected components, and we get 3. So we can do the 3 moves. So basically, we can use the disjoint set to do this problem. Our task is to find the number of the connected components. Also, we can use the DFS, depth first search, and in this solution, I will use the disjoint set. Let's define the disjoint set. As we will use some optimization, so we need to record the size, and of course we need the root array, and we also need the count of the connected components. The size array means which each node how many children it has, because when we do the union operation, we can choose the root which has the smaller size to union to the root that has the larger size, which is union by rank. So in this case, we can optimize the disjoint set. Okay. So public disjoint set, and we will given it an n, and we initialize to the n, and the root equal to the n, and the count at the beginning will be 0. And we will initialize each root to at first, each node parent should be itself. So for int I equal to 0, I less than n, I plus the root I will equal to I. And then we should define 2 private operations, and one is the the first will be the find. Given a node, we will find it, and in this case, we will use the path compression. So if the root x not equal to x, we will let root x equal to find root x, and finally we will return this root x. And we will also need a union operation. We will pass to a node, and we will first get root x equal to find x, and the root y will equal to find y. And if root x already equal to root y, then we just return. And then we will compare the size. If size root x less or equal than size root y, we will change the root, because the root x has smaller children, so less children, so we just change the root x to the root y, and at the same time the root y will increment by 1. If not the case, then we will let root y equal to the root x, and the same increment the root x plus. And every time we do a union, we should let the counter minus. So I made a mistake. At the beginning, the count should be n. The number of the kinetic components at first will be n, and every time we union, we let the kinetic components minus 1. Okay, so in this case, what will we do? We'll first get a disjoint set dsu equal to new dsu, and we will need the n equal to the stones dot length, or number of the stones, and n. And then we iterate the stone. For int I equal to 0, I less than stones dot length I plus plus, and for int j equal to I plus 1. For the other stones, j less than stones. Stones size length j plus plus if they share the same row or column. If I 0 equal to stones j 0, or the stones I 1 equal to stones j 1, then we'll let DSU union the I and j. And finally, we just return the n minus DSU dot count. Okay, thank you for watching. See you next time.